Hello everyone, you are welcome to my YouTube channel. This is Python for Chemical Engineers. In today's episode, we will be discussing quadratic programming and mixed integer linear programming. And for this discussion, we will be solving these two problems using the package SciPy and GEKKO. I've talked about the package SciPy in one of my videos. You can check that out using this link. Let's quickly move straight and go to my browser. And here we'll run through the package GEKKO very briefly. First, GEKKO is a dynamic optimization package written in Python. And so you can read through what GEKKO can do. Here they talked about the four variables that you can define in GEKKO. We have the constants, the parameters, variables, intermediates. Okay, and they are firstly the standard types of variables that you have in GEKKO. Also, we have the fixed variable, the manipulated variables, state variables, and control variables. These variables are what features you can use, in facilitating your dynamic optimization problem formulation, especially when you are solving problems that have to do with optimal control. You can just read through this. I don't want to spend too much time discussing this, so that we'll go straight to how we can use the package. So here are all the options and ways you can call parameters, variables in GEKKO, likewise intermediates. Let's go through the modes of solution, which is very, very key in using the package GEKKO. There are about 9 mode options, okay, which is called the I mode. There you define it by model.option.imode to define the specific problem you want to solve. So the problems are classified or categorized into three broad classes. We have simulation, estimation, and then we have control. Now, under these three classes, we also have the non-dynamic, which is under there you have the steady states. We are solving the steady state problem. The I mode is 1. You have the MPU state, also steady state, but under this estimation, we have the MPU, and then you have the RTO, which is the real-time optimization, also steady state for control. Then we have another subclass which is dynamic and simultaneous. Here, I mode 4 is simultaneous when you are simulating or solving problems that have to do with deep simulation. We'll see that very shortly. I mode is 5 when you are dealing with estimation, and I mode is 6 when you are dealing with a control problem. And then the second last subclass there is dynamic sequential. So you can either use dynamics simultaneous or dynamic sequential. So we have can switch between I mode 4 and 7. Under simulation, under estimation, you can switch between 5 and 8, and under control, you can switch between 6 and 9. We're going to see when we need to use all of these options. And this is how you define the dynamics of the equation using the GEKKO m dot equation, and then you pass the equation in parentheses. These are defined as, for instance, you have the x dt, you just the x dot dt with the open and close parentheses, the derivative. And so that's for the dynamics. Talked about the simulation, the modes you can use when dealing with simulation. Remember, mode 1 for steady state, you can either solve simultaneously. So what it means that you are solving the equations simultaneously, or you can solve them in sequential forms. Okay, that's why I mode is 7. But like the deep modes will give you the same solution. Either you use sequential mode, which solves at one time step, or you use the simultaneous mode that solves at all time step with one at one solve. So that's the I mode. For estimation, like that's the model predict parameter update MPU. I mode is 2 for parameter estimation, and for non-dynamic data when the process is at steady state. So for non-steady state, you can have I mode as well to be 5 and 8. That's under estimation. And that trickles down to control. I don't want to take time to go through all of this. Here you saw an example. This is an example of how you can use GEKKO package to solve for. Here we're dealing with this 5, so we're dealing with dynamic estimation. Then likewise, there are snippets of examples for control, real-time optimization, model predictive control, and all of that. It's you just take your time to go through the package. There are lot and lot of parameters, options you have to tweak when you are using one mode or the other. It also has a deep learning package, it has a machine learning package, it has a chemical library package. There they talked about solver extension. Then you can look at examples. Okay, there are standard examples that they have also used and how to tune the parameters. So having said that, let's go back to our problem. So first I'll be solving this problem using SciPy and GEKKO. So you see the SciPy solution and the GEKKO solution. Then at some point where we cannot find any this solver to solve using SciPy, GEKKO will comfortably handle that for us. So a quadratic programming specifically is written in this format, which is half 1 over 2 or multiply x transpose qx plus p transpose x, subject to x between the lower bound and the upper bound, and then other constraints, equality constraint, inequality constraint. Now, what that means is that for your objective function, if you want to apply quadratic programming to solve any optimization problem, you have to cast your problem in this form. I'll show you how to do that very shortly. So to solve, first of all, we need to import our respective packages. We need matplotlib, we need numpy, then from GEKKO, import GEKKO. And then to use the SciPy, we need the optimization package, and there we need to minimize because this problem has to do with minimization. Even if you are dealing with a maximization problem, you can recast your maximization problem, okay, to a minimization problem. All you need to do is to multiply it by a negative or a minus. So from scipy.optimize, import, minimize. So having imported our respective package into the namespace, let's go to the first problem. Problem 1 says minimize f of x equals x1 squared, 2x squared, x2 squared, 4x, 5x squared. Subject to we have equality constraints and one inequality constraint. Let me mention here before I proceed with this problem that quadratic problem specifically handles problems where the objective functions are not linear. Like you can see in this problem is in quadratic form. So once you have that and you satisfy that criteria, then you can apply quadratic programming to solve this problem. So here we're asked to start the solution at making initial guess for xi to be 1. In other words, guess x1, x2, x3, x4, x5 to be 1 because where I equals to 1 to 5. Now, before we go into recasting this problem, let me just give you a pictorial view of what we are dealing with. Now, what we are dealing with here is simply what we simply need to do is to recast this problem in form of matrices. And so to recast this in matrix form, what do I have? I have something like this. I have a matrix and I have something like this. Here I have this. So I have x1, I have x2, I have x3, I have x4, and I have x5. Likewise, before q, I have a similar. So this is here, this on this part is my x transpose, this is my q, and this is my x. So here you have x1, x2, x3. Don't mind, I'm not using a pointer, so I'm using a mouse to do this, so just pardon me if you look so ugly. So you will notice that when you multiply x transpose, it will return what? It will return x squared. So to have x squared return, so that we have x1 squared, x2 squared, look at the coefficient. We have 1, 2, 3, 1, 2, 1, 4, 5. So what it means that what we have on the diagonal is 1, 2, 1, 4, 5. All other values on the sub-diagonals, upper sub-diagonals, lower sub-diagonals are all zeros. Now, if you have other values okay, which is the other part. Let me go quickly show you that. Go back to this is how we want to cast our problem. You notice that this part where you have P transpose X is not present in this problem. And so we only have this first part. That being said, I want to start by using functions. I'll define objective function that takes what my variable X, it takes P and what? Q. It will return. I'm casting the problem to solve using the format for quadratic programming. So, and that will give me 0.5, which is half multiplied by X. Now, instead of using X transpose here, I'll use the at symbol that performs that operation, which is the dot multiplication. So I have X at Q at X plus P at X. So that defines this first part. And then I'll define my constraints such that you have my variable x, a, and b, both here. Remember, we are casting the constraints with respect to this. So a equality multiplied by x will be cast into matrix equals to b equality here. B after the equality sign is 0. Likewise, a less than b. Now notice that in this problem less than or equal to, but here our inequality constraint is greater than or equal to. It doesn't really matter. So that gives me this expression here by transferring b across the equality and inequality constraints. So I'll have a b and I'll return a multiplied by x, which is a dot x minus b. Now, what I will do is to have that in my namespace. Now, I will move straight to the next cell and then define the value for Q. We have said earlier that Q is this when we cast it in matrix form. So I need to get the diagonals of this. So to get this using NumPy, simply have Q equals. Now notice that we want this value to fit exactly in here. And how do we get this half? Is to multiply Q by 2. So that when we cast into this point, 0.5, this half multiplied by 2, okay, what we have here will return this expression this way. And so that's why I have 2 times np dot diag. So diagonal, that's what it means. 1, 2. The value is 1, 2, 1, not 3. So we should have 1, 2, 1, 1, 2, 1, 4, 5. The next to define the A equality array, which is np dot array. Okay, we have, look at it, x1, x2, x3, x4, x5. So it's this 2, 1, minus 4, 1, minus 1. That's what you have here. The other one is 5. Notice there is no x2, so it is 0. The coefficient is 0, followed by 2, 1, and then minus 1. That's why I have 5, 0, 2, 1, minus 1. Okay, define that as an array. That's a 2 by 1, 2, 3, 4, 2 by 4 array. Then B equality for both is 0, 0. Next, define A inequality. It's just 1. So we have 1, 2, 1. So that's the array. And then B underscore inequality is 6. So define the array. Having defined this, we will initialize our initial values x naught, np dot ones 5, because we have to assume the values to be 1. So we have 5 variables. So ones 5 will give us 1, 1, 1 into the length of 5. You need to define our first constraint here if you want to solve this problem using SciPy. Constraint 1, define that as a dictionary. So we have type. What's the type? Passing inequality. What's the function? Constraint. We're calling this function constraint. Now, we have in this constraint, it takes arguments a and b, and that's why I have to define args, and I'll pass in a equality, a underscore inequality, so to say b underscore inequality. I'll repeat that for constraint 2. Type is equality, function constraint, args, a underscore eq, b underscore eq. Remember that I passed them in as tuples. Pass them in as tuples. If you have just one, then it doesn't really matter. But once more than one, you pass them in as tuples. Then I'll define adjust an option. I want a maximum iteration of 1000. Then you also need to define the bounds. So I want x to be bounded between 0 and infinity. I don't want a negative value for x. So non-negative value for x, as I have 0 np dot infinity. But I need 5 of the bounds. And so I'll put them as a tuple followed by a comma and multiply by 5. This will produce 5 of these tuples, 0 np dot infinity, in 5 places. Having done that, I can then call my solution, which is minimize. Remember, minimize from SciPy. So I'm solving this problem with SciPy. Minimize, pass the objective function in. You have to find that your x naught constraint. We have two constraints, so you pass them as what? As tuples, const 1, const 2. What is my bounds? We have defined our bounds, my args. This time around, I'm passing these args this way because these args actually refers to the arguments that you have in the objective function. Remember, we have to pass in two other arguments, q and p. For the constraint already has been defined in the constraint dictionary that we defined above. Then what method should we use in SciPy? We should use the sequential least square quadratic programming method, and then options here is options. We will run this and let's see what we have. Solving, already solved. Now let's print our solution. I have printed solution.x to see my optimal values of x, and then solution of function, which is give me the objective function. Run that. That returns my x value. We can see the value of x. X1 is this, x2 is that, x3, and x5 is 8.3 to the power of minus 15, which is more or less 0. And then this is the optimal value, which is the minimal value, 12.84. Now let's proceed again to solve the same problem using the package GEKKO. Here we define GEKKO remote equals true, or if you don't define remote to be true, by default remote is true. Then I would call an array x. Okay, I'll define m dot array. I have x array, I have 5 of them, so I'll define m dot variable 5. The lower bound is 0, upper bound is 10. It doesn't really matter. You can also use mp dot infinity here. Then I'll define the problem, which is a minimization problem, m dot minimize, define cast, because of course the definition I have is for my quadratic programming. Now, what I will do next is the x array that I've defined. I don't want to call x by taking each individual value, x of 0, x of 1, x of 2. So I will simply say here x1, x2, x3, x5, x4, x5 equals to x. So I'll unpack the values. So I'll be able to define my equations and write my equations exactly the way I have it in the problem. And so that's why I'm doing this. I then define equations. Now notice that define your equations one after they have equations, m dot equation for the first equation, m dot equation for the second one, for the third one, for the fourth one. But you can also define them as equations and then pass them as array. Now that I have m dot equations, you open a square bracket, you define the first equation, write the second equation, and write the third equation, passing the exact equality and inequality constraint. Close it, and then m dot solve display equals false. I don't want to display the solution. If you click that, it runs. GEKKO uses the remote server to solve, and in a short while returns the answer. As you can see, the output is good. So I'll print the values of x and then print the optimal value. Let's see what we have. Returns an array, and you notice that what compare the two values have exactly the same result. Also, this also refers to this value, okay, being 0 to the power of minus 6, 0.000 down, and the optimal value is 12.84, 12.805. Same. So you can see that using GEKKO, we even have the problem, being cast in a more shorter form. GEKKO understands the constraints, so we don't have to define the, constraint type and all of that we have done when using SciPy. Also, we don't have to define the method. Gecko dynamically understands this problem and solves it by minimizing the functions subject to those constraints and then outputting the results. Now, let's go to problem 2. Also, here we have the minimization problem. Also, notice here that in this case, we have a quadratic objective functions also combined with linear term and then an extra 10 plus 50 here. We're going to cast this like we did for the first problem and then use SciPy and then Gecko to solve like we have done before. Now, let me quickly go back and recast this problem again. Well, you would first of all associate these two values that has it squares the 0.4 x squared plus x2. In this case, we have it this way. It is x1, x2, no, x1, and then it is x2. And then we have our matrix. Likewise here, we have x1, and then we have x2. Now, plus the other part, P transpose multiplied by x. So x1, x2. Now, for this, we have minus 0.4 and x1 squared and x2 squared. That forms the diagonal 0.4, and here we have 2. The other values on the leading and diagonals are all 0. Now, for the p value, we'll return back what we have. We have minus 5x1 minus 6x2. The transpose will simply give us minus 5 and minus 6. Then we have a last term plus 50. This term is a constant term. So what we do in solving the optimization problem, we will leave out that constant term. But after solution, for us to obtain our minimal or optimal value, we'll then add that constant value. That's the trick in solving this problem. So that's why define, like I did earlier, objective function, constraint, and then come here was my q. Q should be half, so you multiply by 2, and the array is 0.4001. That's exactly what we have here, 0.4002. Okay, 0, not 1, 2. So again, we have done that. Define p minus 5 minus 6, like as we have seen. The next thing is to define the the matrices of the constraint. They are all inequality constraint. We write this. We have minus x1 plus x2 greater than or equal to 2, and that's why I have minus 1 1. The next one 0.3x1 x2 greater than or equal to 8, 0.31, and then the b array will be 2 8. X naught is 0 0. First of all, I'm using SciPy to solve. So constraint type, inequality function constraint. The args are a, comma b that we have defined here. Was our bounds 0, comma 10. We have two tuples of that because we are told that x1, x2 should be bounded between 0 and 10. And then maximum iteration 1000. Of course, here I call result equals minimize. Same like we have done in the first problem. So run this. My objective function. Oh, sorry, I need to run this cell first. So I have it in my namespace. Then I can run this. The results is done. Then I rerun this. It returns x1 value, x2 value, optimal value is at 3.278. What I've just done here is that when you in SciPy, you just call result.x and then take the first item to have the value printed out this way. Likewise for x1, which is x2, based on Python indexing. So solving the same problem with Gecko, what we have just called Gecko remote is true. Define a variable m.array, m.variable. We have two of it. Lower bound is 0, upper bound is 10. Define the minimization problem. Then, but I will do something here. There's a trick here to handle this inequality in Gecko. what I will do is to define the term AX, which is the product of the matrix A multiplied by the variable X. I will call that AX. So because I want to lump these two inequality together with a single loop. So I will come here and say m dot equations. I open it AX greater than or equal to b of I for I underscore comma underscore in enumerate b. So I'm actually looping here but using enumerate to make it more efficient. Then m dot solve display equals false. If we run this, Gecko solves it in a short while. We'll have a result. We already have a result. Then we can print the values of x and the optimal value. What do we have? We run this. It returns the value of x is this and the optimal value is that. Now, mind you, this optimal value actually shouldn't be this. Why? Because we omitted the constant term. So the optimal value should include the constant here and say this should be plus optimal value objective function plus. So if we run that, the optimal value should be 83.278. We should have also implemented that here when we solved with SciPy. So we'll move to the next problem three, same format, but notice here that if you expand what we have here, okay, or we also have a quadratic expression. So first of all, define the objective function if you want to solve with SciPy, and this is the definition. The constraints are these. We have two constraints: constraint one, constraint two. Okay, this is the first constraint. The first constraint here is inequality constraint, but I've already returned that as just equality constraint by transferring 25 across. The second constraint, likewise, I'll write this equals 40. And notice what I did here. I simply used a sum function here, and then with a loop, sum xi all squared for I in range 4 minus 40 does that for all of these. Then define x initial, which is x naught 1, 5, 5, 1, and my bounds are between 1 and 5. I have 4 of those bounds because I have 4 variables. So here, define the dictionary for first constraint. The type is inequality, function is constraint. We don't have arguments. Define the second constraint. So I can have this in my namespace. I have this in my namespace. The next thing is to call solution 3, which is minimize, pass the objective function in, x naught equals x in it, constraint equals the tuple of cons 1 and cons 2, bound equals bounds, and method is x, l, s, q, p. So we can print solution.x, solution.function, and that returns the solution for us. The optimal value is 153.44 or 3.45, 1.45, and the optimal or minimal value is 28.44. How do we solve this problem using Gecko? Now, to solve this problem using Gecko, I don't want to recast that into a quadratic programming problem, so I just solved directly with Gecko. I want to show you two sides to it, that you can either recast your problem in the form of a quadratic programming problem, or you can solve it directly by just defining the functions and running them either with SciPy or with Gecko. So here I have M called Gecko, remote is false. I want to solve that without the remote server. Then define x1, x2, x3, x4 equals m dot array of m dot variable. How many of them? 4. Value with an initial guess of 1. So 4 of them will have initial value of 1, lower bound 1, upper bound 5. Now, because the initial value of the second and the third variable are 5, I would come here and define x2 dot value equals 5, x3 dot value equals 5. The idea behind this is to recondense defining the variables separately. So I will overwrite the value I've initially defined here as 1 to be 5. Then next, define my m dot equation, the first equation inequality constraint. Define the second equation equality constraint, and then define my minimization problem. Then next, m dot solve display equals false. Print the values, print the objective function. If we run this cell, it returns the answer 1, 4, So you can see gecko value is more or less almost the same as the result we got from these, but with a little slight deviation, just some based on the approximation value. Actually, here the optimal value here is 17.01, and optimal value here is 28. Let me take a look at my definition of my problem to see if I didn't make that. Okay, I think the problem should arise from the way I define the function. Solution will return the same answer. So next we want to talk about mixed integer linear programming and MILP with SciPy and with GEKKO. So to do that, we have to from SciPy.optimize import MILP, from SciPy.optimize import linear constraint. We already have Gecko already imported in our namespace. So let's go to problem 4. Here we are asked to solve this optimization problem, or rather minimization problem. F of x equals x1 plus 4x2 plus 2x3 plus 3x4, subject to these two inequality constraint, where x1, x2 must be greater than or equal to 0, non-negative, and must be an integer, while x3, x4 must be greater than or equal to 0. In my next two episodes, I'm going to pick specific problems, practical problems, okay, that we're going to recast in this form and solve exactly using what we have learned in this video. So that will take us straight to the solution with SciPy first. So the mixed integer linear programming problem is of this form: minimize C transpose X subject to lower bound and upper bound. Okay, here the non linear constraint, and then the lower and upper bound on the variable, where X is a member of Z, X is also member of Xi, I is a member of Xi. All these are just notations to define that X is within that set of integers and real numbers. So let's move into the problem. Here we are going to be solving the mixed integer linear programming problem with integrality option. So first of all, define your C. What are my C? The coefficient of variables in the objective function 1, 4, 2, 3. So C is 1, 4, 2, 3. You transpose that and you multiply that by X to return this expression that we have here. Next, define A. A is the np.array. Of course, A are the coefficient of what? Of the inequality constraint that we have here, of the coefficient of the variables in the inequality constraint. So we have -1, 3, -1, 2, 1, 3, 1, 1. So we define that here. Then BU refers to the right hand side, okay, across the inequality constraint 2, 3. Now, to solve this problem, we'll first of all have to convert the inequality constraint to linear constraint. And that's why we have imported linear constraint from SciPy.optimize. There is a second way of doing it, when you use linear programming, but I don't want to use that method. It's quite popular. I want to use this directly as MILP is part of SciPy new package in updated version of the site. Constraint equals linear constraint A, comma BU. Then we are solving, we call MILP C, define the constraint. Constraint is constraint. Integrality defines the variable that we know to be an integer. So x1, x2 is an integer, so you turn that on as 1, 1. X3, x4 are not integers, you turn that as 0, 0. So SciPy solves knowing that x1, x2 are integers, while x3 and x4 are not integers. So run this cell, and what do we have? Return 0, 1, 0, 0, and the optimal value is 4. Let's see the solution with, you can actually unpack the value of x. I don't want to spend time doing that. So let's solve that problem with GEKKO. So here we call GEKKO x1, x2, m.array 2 of lower bound is 0, integer true. X3, x4, m.array 2 of that, lower bound 0, integer equals 4. So here I've turned on the integrality option for x1 and x2 and turned it off for x3 and x4. The next, I just define my equation as usual in Gecko, non inequality constraint. Then call the minimization problem, and then turn on my solver option to be 1, and then we can extract the values of x. And what do we have? 0, 1, 0, 0, and the optimal value is 4. Right here is a practice problem I want you to undertake, and you can either solve this directly in Gecko or recast this problem as a quadratic programming problem, and then see how well you understand what we have discussed in this video. With this, we have come to the end of this video. Like this video, share this video, and if you are new to my YouTube channel and watching this video for the first time, do not leave without subscribing to my YouTube channel. And have any question, please leave it in the comment section. I will link to the download of this notebook in the description section. Also, if there's any other topic you want me to discuss in relation to Python application to chemical engineering, you can also leave that in the comment section. Thank you for watching. See you in my next video. Bye.